Okay, so in this screencast, I want to talk about global climate change as we observe it in the geologic record and how we can use what we observe there to try to assess where things are going currently. So let's remember that global climate change is primarily a function of carbon dioxide content in the atmosphere. So when circumstances change, say volcanic eruptions put a lot of carbon dioxide in the atmosphere, or certain positive feedback loops put more carbon dioxide in the atmosphere, carbon dioxide tends to cause the atmosphere to warm. And when that happens, we get a certain pattern of changes geologically. So let's just take a look at what some of those are. So if we take a look at ice cores, we talked about in a previous screencast, we can look at ice cores and make an inference about what the temperature was based on ratios of oxygen 16 to oxygen 18 in water. When we look at this, what we see is that there have been quite a bit of changes in Earth's temperature across the past, and that these changes are basically the result of two things primarily, and that is the amount of carbon dioxide in the atmosphere and the amount of albedo we have as a result of snow and ice reflecting sunlight. And these combinations of two things can cause the temperature to go up or it can cause the temperature to drop. So when concentrations of carbon dioxide are high, the temperature goes up and ice melts and albedo goes down. But there's other times where concentration of carbon dioxide goes down, albedo goes up because there's more snow, and in that case, the temperatures can drop significantly. Now, aerosols are something that I suppose we should have said more about earlier, and I want to talk about them now. So aerosols, which could include, particulate matter that humans put in the atmosphere through, pollution, but right now let's just focus on the geologic past. So these primarily would come from volcanic eruptions. It could also come from wind-driven waves that put salt spray in the air. But right now, let's just focus on the main one would be volcanic eruptions. So powerful volcanic eruptions like, say, Mount Pinatubo or Mount El Chichon in the 80s or Krakatoa. When we have a large volcanic eruption, a cataclysmic one, it puts a significant amount of aerosols into the stratosphere. And in the stratosphere, remember, there's not any wind. So these things just sort of blanket the Earth, and they can stay up there for quite a bit of time. And we know with all the recording we were able to do in terms of climate data in recent years, when Pinatubo erupted in like 1991, we saw a significant and pronounced diminishment in global temperatures in the following year. And that was just one eruption. Conceivably, you could have multiples of those. And if that happened, and you got enough up there, you got a significant enough drop, then you could end up getting a positive feedback loop that worked in the opposite direction towards cooling. In other words, you get more snow, and if you get more snow, you get more albedo, so the temperature continues to drop, which makes more snow, which makes the temperature drop more, which makes more snow, and so on. So that's presumably how ice ages get started, from aerosols, and at a time when there's not a lot of carbon dioxide. So, but for the most part, carbon dioxide is the main player. So if we look at graphs of concentrations of carbon dioxide, which we can get from ice cores, and we compare it to temperature changes, which we can get from tree rings and ice cores and shell samples, what we see is there's a very tight correlation between the two, right? So when carbon dioxide levels are high, temperatures are high. When carbon dioxide levels drop, temperatures drop. When carbon dioxide levels go up, temperatures go up. When carbon dioxide levels go down, temperatures go down. All right, so there's definitely a very clear correlation in the fossil record between those two variables. Now, it's worth noting, though, that if we keep in mind, we don't have time machines. We're basing this primarily on oxygen isotopes when we go into the far past. But when we do go into the far past, here's what we notice. There were times in the past where the temperature of the planet was significantly warmer, like by, say, 20 degrees Celsius more than what it currently is. That's a lot, okay? So we see is there are times in the past where it's been very hot. So basically, in this graph here, this line here represents a global temperature at which ice caps can form. And when you have ice caps, that's considered to be an ice age. We're currently living in an ice age. right? It's not it you know it's in an interval of recession, right? But we're still, it's like the glaciers are receding, but it's still considered an ice age. But there's been much of the worst historic past, geologic history in the past, where that was not the case. It was too hot for that, and so we can see that global climate changes significantly over time. Now, climate deniers will look at this and they will tell you, well, there you go, the climate just changes, and so it's not our fault. Just keep burning those fossil fuels, and don't tell those people they have to do anything. Don't talk to me about carbon credits or whatever. Don't talk to me about carbon tax. But that's not very legitimate, because these periods of time are vast, and what we're seeing now is happening over a very short period of time. So it shows a lack of scientific understanding to say, yes, because these temperatures were so high in the past and it wasn't our fault, that just because they're changing now, maybe it's not our fault. It's our fault, and we need to own it and deal with it, and we can. All right, but anyway, let's just keep going here. Now, when an ice age occurs, right, in these periods of time, when you basically have increased albedo and decreased carbon dioxide, the continental ice sheets advance. So right now, in the northern hemisphere, there's only continental ice here in Greenland. There isn't any here in North America, and there isn't any at the pole because it's covered with water. There is a significant amount of continental ice in Antarctica currently, as there has been in the past. But if we were to go in a time machine and go back 13,000 years or so, we would see that continental ice did not just stop here. It continued all the way down here into what is now the United States. Much of Northern Europe was buried. A lot of what is now the Himalaya Mountains, it came all the way down to the bottom. Korea, no. Okay, there's no evidence that Korea was buried under, but the Andes Mountains and so on. So there was a significant advancement of this ice, and along with that comes a certain amount of changes that we expect in terms of other aspects of the world. And one of them is sea level, because in order to make these glaciers, you had to take water out of the ocean, and then it lands as ice. And this ice we're talking here is, maybe as much as like 3,000 meters thick. I mean, it's significant. Okay, and so that all that ice has, is going to lower the oceans. Okay, and so here's a graph of the oceans in the past. So here we are now, but during the last ice age, they were down. Look at that, 120 meters lower than they currently are. That's a lot of change. And then at other times they've been up to basically where they are now, maybe even a little bit higher. So as glaciers advance and melt, sea level goes down and then up. Right? So when glaciers advance, they go down. When glaciers melt, it goes up. So let's just look at this. This is a Google Earth map of the Aleutian Islands, okay, which extend from Alaska across to Kamchatka Peninsula. And if you see here, this is what's called the Continental Shelf. This is continental land that's submerged currently, all right? And it's not very deep. It's less than 120 meters deep. And so basically, when we took all the water out of the ocean to make this continental glaciers that extended all the way to here, all of this was exposed. So let's think about what happens to life on Earth when you make those kind of changes, right? So if you basically take all this currently submerged land and now you expose it and make it land, well, you know what's going to happen? Succession is going to happen. Life is going to move out onto there, and it did. And so this was all forested land. You could literally walk across here. And humans did. That's how they got to North America. 10,000 years ago, they walked across because it was just land. There wasn't this Pacific Ocean thing in the way. And so that allows for changes in where the biomes are located. It allows for species to move from one place to another. I mean, you could argue humans were an invasive species. When they got to North America, they played havoc on a lot of the vertebrate species there. So let's just look at, I put together a couple of my famous artwork here. Let's see how this works. Okay, so let's look what happens when sea level drops. Okay, so what are the biotic changes we would expect from a dropping sea level? Okay, so here's sea level, and we have coral reefs growing in the shallower waters of the continental shelf. The photic zone extends down to here, below which we have the aphotic zone. Okay, now sea level is going to drop. I'm going to leave the land where it is, but I'm going to let sea level now drop, and it goes out to here. Well, what happens is we expose the continental shelf, and so primary succession will occur, and these trees will grow out there. The coral that was here obviously is left high and dry, is going to die. Now the truth is, it's not just going to this process. If it happens slowly enough, gives the coral time to migrate with it. And although this coral will die, other corals will grow in other places. If it happens too rapid, that may not happen. Another thing that can happen is where we had a photic zone here, if sea level drops enough, that becomes photic zone. So this area down here that was not very rich in life suddenly becomes rich in life, and there's a lot of nutrients there. So we see these shifts in the biosphere as a result of these changes that happen in terms of sea level. Well, but when climate change changes the amount of glaciers that are inhabiting the land masses. Now carbon dioxide increases, and these glaciers melt, which reduces albedo, which creates this positive feedback loop, which causes these glaciers to melt maybe all the way away. That seems to be happening right now, accelerated by our behaviors, this anthropogenic carbon dioxide. Naturally not, here's what's going to happen. All that water is going to go into the oceans, and the oceans are going to get warm, and thermal expansion is going to occur. And so the sea level is going to go up. So now what we have is this. So here's what we have right now. Let's focus on a couple of things here. So let's just say I have a system here where there's an estuary. Now, I feel like I should have said more about estuaries before. An estuary environment is very important. Remember, it's at the mouth of a river. This is like salt marshes where the rivers meet the ocean. And these rivers carry all this nutrient-rich silt down, and they deposit in this delta-like area with all these marshes growing, right? And so what happens is in that area, there's a lot of productivity because you have shallow water, which is photic, and you have all these nutrients. So it's basically the rainforest of the ocean. And it's also the nursery for most marine fish species will raise their young, or will have their young grow in this area, okay? Now, and let's just say the sea level is low enough that the bottom is photic. Okay, so we're getting light in here. Now the glaciers melt. What happens is as the waters advance, they're going to erode this estuary environment. Now, chances are it will move back a bit, but it may get eroded away, right? And as that happens, now all these nutrients are going to move out into the ocean. Instead of getting captured in the estuary, they're going to go out into the ocean. So by adding nutrients to the ocean, we can expect to have eutrophication. Also, too, what we find is that where the bottom was photic now is deep enough that it might become aphotic. Again, we're going to make some significant changes in the marine environment and into the estuarian environment by changing sea level. Now, let's throw in the mix that humans like to live here. And so a significant amount of the human population is living in this area. So when sea level changes, there's a lot of displacement of non-human species as well as human species. Now, right now, there is a very, very, very significant rapid change in both CO2 and methane levels, CH4, in the atmosphere, and it is causing the global temperatures to rise very rapidly and causing these continental glaciers to melt very rapidly. And so we can expect to see some very significant changes, both in terms of shoreline, estuarine ecosystems, nearshore ecosystems, and terrestrial ecosystems. Because when you change you're not just changing sea level, you're also changing rain patterns, wind patterns, and so just the whole climate. And so remember, the biomes are based on the climates that are typical for their area. But when you change what's typical for that area, you're going to redistribute where biomes are located. And if this happens slowly, the species adjust with it. They move with it. They adapt with it. They evolve with it. But if it happens very rapidly, it's just too rapid that they can't really adjust to it. So what happens? Almost done here. I'll be done in 1 second. So let's just look at this. This is the United States during the last ice age. So here's where all that ice was. As a consequence, look at this. This area here was all this sort of temperate woodlands. It was basically redwood forests. If you look, we had tundra all the way down into here. We had taiga extending all the way down into what's now Nebraska. And now look what happened when the glaciers melted away. It made this total shift in the climate, and so this area here that was like redwood forests, it became basically desert. If you've ever been to Utah, it's pretty much a desert. This tiny grassland really extended. Where we had taiga here, the taiga moved all the way up to here. So basically, we redistributed all this life. Many, many, many species went extinct. Now that took place over a long period of time at the end of the Pleistocene glacial epoch. Right, what's happening now is it's much more rapid than that. So that it's pretty obvious that most species are not going to be able to adapt. And so what we find is when these changes happen very rapidly, these changes in biotic and abiotic factors are too rapid for species to adapt to or to evolve to, and that typically leads to extinction. So species that are left in a situation where their habitat is gone and is no longer where they are, you can expect to have a bit of species extinction. And unfortunately, congratulations, you happen to be living in the greatest extinction event in the history of the world that we're aware of. So this is a graph, and you can take this with a little bit of a grain of salt, but basically it's trying to show you that if you try to link, extinctions to temperature change, what you see is that the rate of temperature change in these past extinction level events was such that here, like the Eocene one, the most recent extinction event, we had like, look, 5-degree change over 5,000 years. The one that marked the end of the Triassic, which was the big one, temperature rose 4 degrees over 10,000 years. Right now, the temperature is just changing so fast that it's just unthinkable. So, look, if like whether or not these temperature changes were the cause of those extinctions is a matter of scientific debate. But it does seem that some of those extinctions probably were due to that. And what we see now is, man, it's just crazy. So this current climate change is going to cause a lot of species to go extinct. It's unavoidable. So that's one thing you definitely need to know about this. I think that's the end of my screencast. Thank you for listening. My man Rob Paul wants me to drive him home. My wife would like to see me. So thanks for listening. And I'll see you guys when we get back from our break.